Hello students, today we shall see linear differential equation of second and higher order with constant coefficients part 2. That means today we shall see what is particular integral, what are the rules of finding particular integral, and then some explanatory examples how to solve linear differential equation with constant coefficients when right side is not 0. Right side will be a function of x alone. So first we shall consider the second order linear differential equation. That means we shall see the method of solving d square y by dx square plus p1 into dy by dx, p1 into dy by dx plus p2 into y equal to capital X, where p1 p2 are constants and capital X is a function of x alone or maybe constant in special case, but capital X is not 0. When it is 0 we have already solved. Now let y equal to phi of x comma c1 comma c2. Phi is a function of x and arbitrary constants c1 and c2. This is the general solution of the differential equation d square y by dx square plus p1 into dy by dx plus p2y equal to 0. Same equation as in number 1, only right side is 0. When right side is 0, how to solve we know. So suppose y equal to phi of x comma c1 comma c2 is the general solution of this differential equation number 2. And let y equal to psi x is a particular solution of the differential equation number 1. Y equal to psi x satisfies this differential equation number 1, means when we put y equal to psi here we shall get capital X. So it satisfies, it is a particular solution without any arbitrary constant. Then the general solution of the differential equation number 1 is given by y equal to phi of x comma c1 comma c2 plus psi of x. Because why it is solution? Because it satisfies the differential equation number 1, which is of order 2. Differential equation number is of order 2 and contains two arbitrary constants c1 and c2. This relation contains two arbitrary constants. So it is the general solution. And why it satisfies, we can see if we put y equal to phi plus psi, actually it is phi plus psi you can call as a function, then we shall get LHS equal to left hand side of the differential equation 1 d square phi by dx square plus p1 d phi by dx plus p2 phi, and then another will be with same d square psi by dx square p1 d psi by dx plus p2 psi. But this part is 0 because phi is a solution of the differential equation number 2. So when we replace y by phi it is 0, and this part is a particular solution. This psi is a particular solution of the differential equation number 1. So we shall get capital X. So it is 0 plus x means equal to x. That means right side of the differential equation 1. So y equal to phi plus psi satisfies the differential equation number 1. That's why it is general solution, because it contains two arbitrary constants, it satisfies. This is the definition of general solution of a second order linear differential equation or second order differential equation. In this case, this phi of x comma c1 comma c2, first part of the solution, is called the complementary function. In short, we shall write always CF, complementary function. And psi x is called the particular integral pi. In short, we shall write pi, particular integral pi of the differential equation number 1. So that the general solution of the differential equation number 1 can be written as y equal to CF plus pi. How to find CF we know, only now we shall learn how to find pi. Okay, when right side is 0, the solution will be called CF. Note, for third and higher order differential equation of above type, means with constant coefficients, right side not 0, the method of solution is similar, or you can say same. So what is particular integral? Formal definition or formal process we are writing here. Let the given differential equation of nth order with constant coefficients is f dy equal to x. F dy equal to x. Fd operates on y, where Fd means this nth degree expression d to the power n plus p1 d to the power n minus 1 plus p2 d to the power n minus 2 plus dot 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 pn minus 1 d plus pn, where p1 p2 pn are constants. And d means d dx, derivative with respect to x, differential operator d. And capital X is a function of small x alone or maybe constant, but x is not 0 this time. So this is nth order linear differential equation with constant coefficients. Now we are assigning the meaning to 1 by fd. We define 1 by fd x. 1 by fd is an operator. When it operates on x, what you get? We define 1 by fdx as that function of small x. 1 by fdx as that function of small x not containing arbitrary constants. Important fact, not containing arbitrary constants. This is our definition, which when operated by fd we get x again. That is, when fd is operated on this function 1 by fd of x, 1 by fd when operated on x, this is a function of x. Now when it is operated by again fd, we should get x. That means action of 1 by fd is neutralized by the action of fd, as if equal and opposite forces balance each other like that, as if derivative and integral cancel each other like that. So 1 by f dx is that function of small x, which when operated by fd, we should get the function capital X again, without involving arbitrary constant. That is our definition. That means this line says that this line is exactly same as, see, this line number 1, only y is replaced by 1 by f dx. So this says that 1 by f dx, 1 by fd operated on x, it is an operator. 1 by fd when operated on x, we get a function of x, small x, and this function satisfies the differential equation number 1. Exactly the line number 1 we have got here, and is without containing arbitrary constants, because by our assumption 1 by f dx do not contain any arbitrary constant. So this is the particular integral. It satisfies the differential equation 1. So this is the particular integral. Okay, practically this is the definition of particular integral. Now in particular, if fd equal to d, first order linear equation like that, fd equal to d, then 1 by f dx will be 1 by dx. 1 by d operated on x should be integral of x with respect to x. Why? Because if we operate this by d, means derivative d of integral of x, means d dx of integral of x with respect to x, we get x. We know derivative and integral balance each other. Therefore this 1 by dx should be integral of x with respect to x, because when d is operated here we get x. So by our definition, this definition, when fd is operated here we should get x again. So here when d is operated on 1 by d of x or integral of x with respect to x, we get capital X again. Therefore 1 by d should be integral with respect to integral of x with respect to x. That is the region. Similarly 1 by d square x will be 1 by d operated on x, means integral 2 times integration of x with respect to x, again integration of this new function with respect to x. If it is 1 by d cube x, it will be 3 times integration successively, okay, and so on. But if it is not d square d cube like that, if it is d minus 1 d plus 2 d square plus d, then what is the meaning, how to find that, we shall see now. Particular case, method of finding particular integral in some particular cases. General method we cannot find any, we cannot give the particular integral of any for any value of x. Some particular cases only we can find the 1 by fd of capital X, that means pi. So if capital X equal to e to the power ax plus b, first rule you may say, capital X is e to the power ax plus b, means right side of the differential equation, linear differential equation with constant coefficient is e to the power ax plus b, then pi will be 1 by fd. Our differential equation is, we have already assumed here, 1 by fd of y equal to x. Okay, fd operated on y equal to x. So pi will be 1 by fd e to the power ax plus b. Answer is answer is, here it is, okay, 1 by fd e to the power ax plus b, and that is equal to 1 by fa e to the power ax plus b, 1 by fa e to the power ax plus b. If fa not equal to 0, f of a not 0, if f of a 0 you cannot put, then what will happen if f of a is 0? If f of a is 0, then this pi will be, it will become 1x you will give here, and below you will write, means of course from this line you will come here directly. If fa is 0, you will come here, it will be x, give 1x in the left side and write 1 by f dash d. F dash d means derivative of fd with respect to d, ordinary derivative, and then it operates on e to the power x plus b, and then you will write 1 by f dash a, means replace d by a, d by a, e to the power x plus b remains, provided when fa is 0 and f dash a not 0. But it may be that f dash a is also 0. In that case the process repeats. Again you will give another x here, again you will give another x here, x square, and this f dash d will be made f double dash d, means again differentiate with respect to d. Again differentiate with respect to d. So f double dash will be coming, and then replace d by a, means x square into 1 by f double dash a e to the power x plus b remains. If f a 0, f dash a 0, but f double dash a not 0. If f double dash a 0, you will again differentiate and the process continues. So this is how we shall find pi if capital X is e to the power x plus b, and we shall see the proof later. Okay, this is the rule. Rule 2, if capital X equal to e to the power x plus b into b. What is b? B is a function of x, small x alone. Then pi equal to 1 by fd e to the power ax plus b operates on v, equal to e to the power ax plus b comes to the left side and d replaced by d plus a, and this 1 by fd plus a operates on v. This is the rule number 2. Now if fa is 0 in the first case, first rule, if fa is 0, you can use rule 2 here. Fa is 0, then for capital X equal to the power x plus b, then pi will be 1 by fd e to the power x plus b equal to e to the power x plus b comes to the left and d replaced by d plus a, and when it operates on 1, means particular case of rule 2 when b equal to 1. So it is an alternative to rule 1. If fa is 0, you can apply it also instead of differentiating and then giving 1x to the left. Next, rule 3, if capital X is x to the power m, where m is a positive integer, maybe 0 in special cases we shall see, then pi equal to 1 by fd x to the power m, fd to the inverse x to the power m. Now this fd inverse we shall expand in ascending powers of d using binomial theorem, general binomial theorem, anything necessary. And suppose the expansion is a0 m1d a2d square dot 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 am d to the power m plus dot 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 up to d to the power m we have expanded, and d to the power m means mth derivative of this x to the power m will be m factorial constant, and higher derivatives will be 0. So only up to d to the power m you have to expand, and then you find differentiate d first 1 time, 2 times, etc. depending on power of d. That will give us the pi. Rule number 4. If capital X equal to sin ax plus b or cos ax plus b, in special it may be sin ax only, cos ax only. Here also, although I have written e to the power ax plus b, in books you may get it is e to the power ax only. Rule is same. B may be 0, special case. Mine one is general. So rule 4, sin ax plus b or sin x, cos ax plus b or cos x, rule same. Pi is 1 by fd sin ax plus b. Now this fd is written as phi d square. Here of course we assume fd is phi d square, that is a function of even power of d. The expression in fd is even contains only even power of d, we assume here for the time being. That case, what we do, pi will be given by replacing d square by minus a square. It is not minus a whole thing square, minus a square. Sin ax plus b remains as it is, provided phi of minus a square not 0. But if it is 0, as before, give 1x to the left side and differentiate this phi d square, phi dash d square, differentiate phi d square with respect to d, and then it operates on sin ax plus b 1 by phi d square, and then you replace d square by minus a square. Sin ax plus b remain as it is, provided here phi of a minus a square is 0, but phi dash of minus a square should not be 0. But in practice we may see that phi dash of minus a square is also 0. In that case, again apply the rule, another x to the left side, again differentiate this phi dash d square, it will be phi double dash d square, derivative with respect to d, and then put replace d square by minus a square, provided phi of minus a square and phi dash of minus a square both 0, but phi double dash minus a square not 0. And even if it is 0, the process continues, and so on. For x equal to cos x plus b or cos x, the rule is same, exactly same. Cos will remain cos, and d square will be replaced by minus a square, etc. Okay, so these are the 4 rules, rather pi in 4 particular cases. E to the power ax or ax plus b, then e to the power ax plus b into v, any function, of course here it is, and then x to the power m, x square x cube, like that, and then sin ax plus b or sin ax, cos ax plus b or cos ax. This is the rule. 4 rules. But here we have assumed phi fd equal to phi d square, but in practice it may not be of even powers of d. So that's why note, if fd consists of both even and odd powers of d, then first we replace d square, d to the power 4, etc. by minus a square square, etc. and then make denominator with even powers of d with the help of a suitable differential operator. means operating by the different, say it may be the differentiated by d plus 1, and also we have used the operator on by d plus 1, like that. If there is d minus 1 in the denominator, then d plus 1 d minus 1 will be d square minus 1 square, like that. But you have to also differentiate by d plus 1. So with the help of a suitable differential operator, and then proceed to find the pi finally, which will be explained in a practical example. We shall see. Now one important result, 1 by d minus a of x. 1 by d of x, we know it is integral of x, but if it is 1 by d minus a is a constant, maybe d minus 1, d minus 2, like that, then the answer is e to the power ax integral of e to the power minus ax into capital X with respect to x. Integral of e to the power minus x into capital X with respect to x, where x is a function of small x alone. Let us see the proof. Let y equal to 1 by d minus a operated on x. The answer is y, means this is a function of small x alone as per definition of pi. So that if we use d minus a here, d minus a of y will be d minus a of 1 by d minus a of x, means it is x, because action of 1 by d minus a is neutralized by d minus a. So d minus a operated on y gives us capital X, means it is dy by dx minus ay, dy by dx minus y equal to capital X. What is this? This is a linear differential equation of first order, and we know how to solve it. Here p means minus a, so integrating factor is e to the power integration p dx, means minus a dx, that is e to the power minus x. Therefore solution of the linear differential equation of first order we have done in class 12 is given by y into if, y into integrating factor is equal to integration of if into q dx. Here q is capital X, right side. So y into e to the power minus ax is equal to integration of e to the power minus x into x dx, and this e to the power minus x, when comes to the right side, it is e to the power ax. So we have proved it, y equal to this. Or you can write integral of e to the power minus x into x dx is as 1 by d of e to the power minus x into x. 1 by d means integral. Therefore y means 1 by d minus of x. We have written y is 1 by d minus of x. So 1 by d minus a, when operated on x, we get e to the power ax 1 by d e to the power minus ax into x. 1 by d operated. Or you can write e to the power ax integral of e to the power minus ax into x with respect to x. So this is the result proved. Now proof of rule 1. What we have written in rule 1, to find pi, we just replace d by a. 1 by fd e to the power ax plus b, replace d by a. So let us see. Let us see the proof. Let fd is d to the power n plus p1 d to the power n minus 1 plus p2 d to the power n minus 2 dot 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 pn minus 1 d plus pn, where p1 p2 pn are constants. This is the operator for linear differential equation with constant coefficients, and that is of nth order. Now d operated on e to the power ax plus b means derivative of e to the power ax plus b, ddx of, it is derivative of e to the power anything is e to the power that thing into derivative of that thing. At ax plus b derivative is a, so by chain rule we get a into e to the power ax plus b. As many times we shall differentiate, that many a will be coming here into only. So again if we differentiate, d square of this e to the power ax plus b means second derivative, so that means derivative of derivative, so it is ddx of a e to the power ax plus b, means a will be constant remaining, e to the power ax plus b differentiated, another a will be coming, so it will be s square e to the power ax plus b, and so on. In general, d to the power n e to the power ax plus b equal to a to the power n e to the power ax plus b. Therefore fd of e to the power ax plus b will be, here fd, d to the power n means a to the power n e to the power ax plus b. P1 is constant rule remain, d to the power n minus 1 will give us a to the power n minus 1 e to the power ax plus b. d to the power n minus 2 e to the power ax plus b will give us a to the power n minus 2 e to the power ax plus, etc. So ultimately e to the power ax plus b taken common, it becomes what, a to the power n, p1 a to the power n minus 1, p2 a to the power n minus 2 dot 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 dot, etc. So this is exactly fd, only d replaced by a, so we have written f of a to the power ax plus b. So what we have got, e to the power ax plus b equal to, this fa comes to the left side, it will be 1 by fa fd e to the power ax plus b, provided fa not 0. Let us assume here fa not 0. So e to the power ax plus b becomes 1 by fa fd of e to the power ax plus b, fd operated on this. Now this 1 by fa is a constant, can be taken inside the differential operator, no matter. So 1 by fa e to the power ax plus b. So what we have got, e to the power ax plus b is equal to fd of 1 by fa e to the power ax plus b. So if we invert, what we get, 1 by fd e to the power ax plus b. If we use 1 by fd operator on both sides, 1 by fd e to the power ax plus b, right side will be 1 by fd operated on fd of 1 by fa e to the power x plus b. Now see, fd and 1 by fd are inverse of one another. Action of one is neutralized by the other. That is the definition. Action of 1 by fd is neutralized by fd. So action of fd is also neutralized by 1 by fd. So 1 by fd of fd will give us what? Only the function. So what will remain? 1 by fa e to the power x plus b. So what we have got? 1 by fd e to the power ax plus b is equal to 1 by fa e to the power ax plus b. Only d replaced by a, provided fa not 0, of course. But if fa is 0, what will happen? Let us see that also. If fa equal to 0, then d minus a is a factor of fd. Surely all of we know, if f of a equal to 0, then d minus a is a factor of fd. Fd is the polynomial expression. That's why d minus a is a factor theorem. And let fd equal to d minus a phi d. What is phi d? Phi d is a polynomial expression of degree n minus 1 in d, because our fd is a polynomial expression, polynomial in d of degree n. So phi d will be polynomial of degree n minus 1 in d, because d minus a is taken common, it is a factor. Therefore 1 by fd e to the power x plus b, when 1 by fd operated on e to the power x plus b, we have to write 1 by d minus a phi d operated on e to the power ax plus b. Now this can be written as 1 by d minus a operated on 1 by phi d e to the power ax plus b. Now 1 by phi d operated on e to the power x plus b gives us 1 by phi a e to the power ax plus b, because already we proved 1 by fd e to the power x plus b is 1 ax plus b is 1 by fa e to the power x plus b. So here it will be 1 by phi d will give us 1 by phi a e to the power x plus b, provided phi a not 0. So let us assume phi a not 0 here. So it is e to the power x plus b, we can write it e to the power ax into e to the power b. So taken e to the power b here, constant, phi a constant taken out, and then 1 by d minus a operates on e to the power ax only. Operator operates on the function. Okay, now already we have proved the result. One important result, 1 by d minus a to the power ax is what? E to the power ax integral of e to the power minus ax into capital X. Here capital X is e to the power x with respect to x. So this is the standard result, already we have proved, 1 by d minus a capital X. So it is e to the power ax integral of e to the power minus ax, again e to the power ax, because this capital X is here e to the power ax. Now this multiplied gives law of indices, gives e to the power 0 means 1. So it is only 1 dx. So 1 dx integral is x. So we have written here x, and here e to the power b and e to the power ax gives us e to the power x plus b by law of indices. So what we have got? X into 1 by phi a. We can write it x into 1 by phi a e to the power x plus b. So what we have got? 1 by fd e to the power ax plus b is x into 1 by phi a e to the power ax plus b. Now let us see. Fd is d minus a phi d, already we have seen. Therefore f dash d, differentiate both sides with respect to d. It will be d minus a, even to b rule, product rule. D minus a will, derivative of d minus a with respect to d will be 1. So phi d plus d minus a will remain, derivative of phi d will be phi dash d. Now put d equal to a, f dash a. Here d minus a will be 0, so simply phi a. So phi a equal to f dash a. Therefore we shall put here 1 by phi a means 1 by f dash a. So see, 1 by fd e to the power x plus b becomes x into 1 by f dash a e to the power x plus b. Now this can be written as 1 by f dash d e to the power x plus b, because when 1 by f dash d operates on e to the power x plus b, by first rule we have seen that d can be replaced by a. So it is there, f dash a, provided of course f dash a not 0. That's why we have written phi a not 0. Phi a not 0 means f dash a not 0, because phi a and f dash a are same, we have seen. So the rule is proved. When fa is 0, 1 by fd e to the power x plus b is x, 1 by f dash d operated on e to the power x plus b. Now if f dash is 0, then the process continues, means 1 by f dash d e to the power x plus b will be, another x will be in the left side, and this f dash d will be differentiated, it will be f double dash d. Provided f double dash is not 0, answer will be x 1 by f double dash a e to the power x plus b. And that means this will be, here better we write this f double dash d is a, replace d by a, replace d by a here. Okay, so this will be a only, 1 by f double dash a e to the x plus, provided f double dash a not 0. But if f double dash a is 0, then again we shall differentiate, another x will be to the left, means the process continues. So the rule is proved. Then proof of rule number 2, d e to the power ax plus b into b, derivative of derivative of e to the power ax plus b into b, u into b rule. So e to the power ax plus b remains dv, derivative of b means dv, plus b remains derivative of e to the power ax plus b is a into e to the power ax plus b, all of you know. So directly we have written here what happens, e to the power ax plus b common and d plus a, and it is operated on b, a into b and d operated on b, we can write. So what happens, see that as if d replaced by d plus a and e to the power ax plus b comes to the left. So again let us see for second derivative, d square e to the power ax plus b, b means d of this right side. So d of this again here u into b rule. So e to the power ax plus b remains d of this. So you have written d of that, plus d plus a b remains. Now d of first function derivative of e to the power x plus b is a into e to the power x plus b. Now again take e to the power x plus b common, and here it is d into d plus a operated on b, and here d plus a operated on b. Of course there is a constant, so a into d plus a taken here, the whole thing operated on b. So here it is d square ad, dA and ad same because a is a constant, dA ad same, so twice ad plus s square. So what is this? This is d plus a whole thing square operated on b. So what happens? See, when d square, here it is d plus a square. So similarly d cube, here it will be d plus a cube, e to the power x plus b to the left, and so on. In general, you can write d to the power n e to the power x plus b into b. When d to the power n operates, we get e to the power x plus b into d plus a to the power n operated on b. So from this discussion, it follows that if we apply this fd on e to the power x plus b into b, we shall get e to the power x plus b f of d plus a. Exactly, f of d plus a will be coming, because see what is fd we have taken earlier, that fd is to be taken here, this. So d to the power n will give us d plus a to the power n, it will be d plus a to the power n minus 1, it will be d plus a to the power n minus 2, etc. when operated on b. So that's why it is f of d plus a and e to the power x plus b to the left. So here directly we have written e to the power x plus b to the left, f of d plus a operated on b. So this rule is, now this is true for any function b. B is any function of x, only it should be differentiable, of course. Any function of b, as many times we want, we can differentiate. Therefore replacing this b by 1 by f of d plus a b, 1 by f of d plus a b is also a function of x, and if we replace b by 1 by f of d plus a operated on b in number 1, we get what? F of d e to the power x plus b, and this b replaced by 1 by f of d plus a operated on b equal to right side e to the power ax plus b, f of d plus a, and b is replaced by 1 by f of d plus a b. Why? Because f of d plus a operated on 1 by f of d plus a b will give us only b. That is the definition of the inverse operator. So these two cancels action of one another. It is not that number is cutting this by that. It is not k into 1 by k like that. It is operator operated on the inverse operator. Okay, so can balances each other, cancel each other, action of each other, so we get b. So what is that? Fd of this equal to e to the power ax plus b v. Therefore if we now use inverse operator, so it will be 1 by fd of e to the power ax plus b will be this part only, 1 by fd, and fd will balance each other. So 1 by fd e to the power ax plus b v into b, we get this answer, e to the power ax plus b 1 by f of d plus a operated on b. On both sides we have used 1 by fd. So 1 by fd means neutralizes the action. It will be, answer will be that it is written here, and here 1 by fd e to the power x plus b written there. Similarly rule 4 can be proved. The proof will not be asked, of course, in exam. Still I have given the proof. So rule 4 proof is also similar. Now let us see at least 2 examples how we apply the rules. So example number 1, solve this differential equation. Right side is minus 2 cos hyperbolic x. So in d notation it is d square plus 4d plus 5 operated on y equal to minus 2 cos hyperbolic x. All of we know cos hyperbolic x is e to the power x plus e to the power minus x by 2. This is definition of cos hyperbolic x. It is not cos hx, it is cos hx. Cos hyperbolic x, we read it cos hyperbolic x. So this is the definition, e to the power x plus e to the power minus x by 2. And if it is sin hyperbolic x, then the definition is e to the power x minus e to the power minus x by 2. That is sin hyperbolic x. Okay, remember. So 2 cancels. Now auxiliary equation is D replaced by m, we know when right side is 0, we write auxiliary equation. So here also we write auxiliary equation. This D replaced by m square plus 4m plus 5. So auxiliary equation is m square plus 4m plus 5 equal to 0. Means y equal to d to the power mx is a trial solution when right side is 0 of the equation 1. So m equal to, we have solved, minus b plus minus root over b square minus 4ac by twice a. 2a means here 1. From class 10 you know the result, how to solve quadratic equation. So minus 4 plus minus root over minus 4, 16 minus 20. So it is 2i plus minus 2i. So it is 2 cancels, minus 2 plus minus I. And I have written I into 1 because alpha plus minus I beta. I want to write alpha and beta form. So alpha is minus 2, beta is 1. Therefore, complementary function. In the last class, whatever we have seen, the solution, now it is complementary function. Because right side of the differential equation is not 0. So this is complementary function. CF equal to e to the power alpha x. Alpha is here minus 2. Bracket a cos beta x. Beta is here 1. So 1x plus b sin beta x. Beta is here 1. So this is the CF. Now PI, particular integral, is, this is our FD here. D square plus 4D plus 5. When it goes to the right, it becomes 1 by d square plus 4d plus 5. Means its inverse is 1 by d square plus 4d plus 5. So our definition is 1 by fd of that. So pi is 1 by fd, means here d square plus 4d plus 5 operated on right side. Capital X here is this, and this minus sign you can take here. So 1 by d square plus 4d plus 5 operated on e to the power minus x. It is also operated on e to the power x. So two parts, two functions here. Now, rule is e to the power ax plus b. Here b is not there, only e to the power ax. A means here minus 1. So replace d by minus 1, provided you do not get 0 here. So if you replace d by minus 1 square, 4 into minus 1, 5, not 0. Derivative is not 0. So you have substituted. And for this part, second part, here ax plus b, e to the power ax plus b, a is here 1. So replace d by 1. If we put 1, replace d by 1, we are not getting 0. So directly we have substituted d1 here and d minus 1 here and got these values. Therefore, general solution is CF, y equal to CF plus PI. So CF and this PI is added. So this is the process for finding PI and writing the general solution. Another example, let us see. Example number 2. D square by dx square plus 2 dy by dx plus y equal to e to the power 2x minus cos square x. In D notation, it is d square plus twice d plus 1 operated on y plus e to the power 2x minus cos square x. But this cos square x, we don't know the particular integral of cos square x. We have seen the rule here in the above rule, 4, rather in rule 4, sin ax plus b. Sin ax plus b cos ax plus b. Okay, we know the pi for sin ax plus b cos ax plus b means sin ax, sin 2x, sin 3x, like that we can find. So cos square x, this square is removed by trigonometry formula, you know. This is half into 1 plus cos 2x. 1 plus cos 2x is 2 cos square x. All of you know. So 2 cancels, means it is cos square x. So we have removed square. So it is e to the power 2x minus half into cos 2x. Okay. Now auxiliary equation is replace d by m. M square plus twice m plus 1. See, m square plus twice m plus 1. Replacing d by m here, we know we get auxiliary equation equated to 0. So it is m plus 1 whole thing square, means m is minus 1 minus 1. 2 times we have written because it is a quadratic equation. It should have 2 roots. Here 2 roots are equal. So equal real roots, we know the solution, we know the complementary function, how to write c1 plus c2x e to the power kx. K is here minus 1. So CF is c1 plus c2x e to the power kx. Okay. Now pi is 1 by d square plus twice d plus 1. Operated on right side. Capital X is here this. It is about 2x minus half cos 2x. Okay. So 1 by d square plus twice d plus 1 is, it should be 2. D square plus twice d plus 1. Okay. Operated on e to the power 2x. 1 by d square plus twice d plus 1 operated on half. 1 by d square plus twice d plus 1 operated on half cos twice x. 3 parts. Right side there are 3 terms. That's why 3 parts we have written here. 3 terms. Now this is 1 plus d whole thing square, we can write e to the power 2x. Okay, this is also 1 plus d square, we can write. Operated on 1, half we can take to the left side, operated on 1. It is the operator, it should operate on something. 1 is a function of x, you can say, constant function. Now here it is, rule is what? See, this is not containing only even power of d, even and odd powers. So already one in the note we have written. What we shall do? D square we shall replace by minus s square. Here cos 2x, cos 2x, cos ax. So a is here 2. So replace d square by minus 2 square, not minus 2 whole thing square, minus 2 square. Okay, and don't replace d by anything, plus twice d plus 1, because rule is only for d square, d to the power rule like that, and half is constant taken here. Okay, and here replace d by a means here e to the power ax, that's why a 2, so 1 plus 2 square, it is not 0, so we can put here 1 plus d to the power minus 2, we can write 1 plus 1 by 1 plus d square, we can write 1 plus d to the power minus 2, binomial. Here we can consider it as x to the power 0. Okay, now half, here minus 2 square plus 1, so minus 3, so 2d minus 3 cos 2x. Now see, it is over, and here 1 plus d to the power minus 2, general binomial theorem expansion, all of we know it is 1 minus 2d plus 3d square minus 4d cube dot 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 dot, it will go up to infinity, operated on 1, and 1 into 1 is 1. 2d of 1, 3d square of 1 means when d derivative of 1 is 0, d square of 1 is 0, all are 0, so only one term, 1 into 1, 1, so that's why it is half. Okay, and here what we want to do, because it is cos 2x and it is d, that's why here we make it d square by what, operating by 2d plus 3. In the denominator we have operated by 2d plus 3, that means we have operated here 1 by 2d plus 3, so 1 by 2d plus 3 and 2d minus 3 will make it 4d square minus 9, but at the same time we should operate by 2d plus 3 in the numerator. It is not that multiplying by 2d plus 3 and dividing by 2d plus 3, you cannot use the word multiplying, you can say operating by 2d plus 3 and also by 1 by 2d plus 3, so neutralizes each other. Okay, everything remains same, but denominator becomes now 4d square minus 9, and d square can be replaced by minus s square, so minus 2 square we have replaced here. Okay, and 2d plus 3 remains, so 2d plus 3 operated on this expression, and here it is okay, it is okay. Here 2 square minus 4 minus 4 minus 16 minus 16 minus 9 minus 25, minus 25 and 2 minus 50, there is a minus sign, so it is 1 plus 1 by 50. Okay, 1 by 50, and 2d plus 3 operated on 2 cos 2x plus 2 cos 2x. Now 2d cos 2x, d cos 2x means derivative of cos 2x, it is minus sin 2x, so minus and into 2, because there is a 2x, so that's why into 2, and already there is a 2, and 3 into cos 2x is 3 into cos 2x. Okay, so what you have got, this 2 if we cancel, it will be minus 1 by 50 sin 2x, another 2 will be there, yes, 1 2 is missed here, 1 2 will remain, 1 2 will be cancelled, 1 by 25, and there 3 by 50, 3 by 50 cos 2x. So with minor correction, this is the pi, this is the pi. See, rule 4 is applied, odd power also made into even power, operating by suitable operator. Okay, therefore general solution is given by y equal to cf plus pi, means cf already we have found this, and pi now we have found, so there is a 2 missed, so this 2 should be there, 1 by 25, or you can say 2 by 25 sin 2x plus 3 by 50 cos 2x. Okay, now here instead of writing this as binomial 1 plus d to the power minus 2, we can do another way. See, in the note I have written 1 by 1 plus d square operated on 1, 1 by 1 plus d whole thing square, 1 by 1 plus d whole thing square operated on 1, means I can write this one as e to the power 0x, e to the power ax. So what is a here? 0. So put d equal to 0, get answer 1. Yes, by binomial also you have got answer finally 1, is it not? Half into 1, here we have written just half, means half into 1, here also it is 1, half will be there. So this is another way, of course. So 2 problems we have seen, some more problems we shall do in the next class, special type of problems. Okay, finding pi, finding cf. Okay, thank you for today.